Thermodynamics, moles and constants. Questions to ponder. What is an atomic mass unit? What is a mole? What is the universal gas constant? What is Avogadro's hypothesis and number? What is Boltzmann's constant and why do we use it? And what are two ways to represent the ideal gas law? To begin, let's remember our ideal gas law. PV equals nRT. We explored pretty closely the relationship between pressure, volume, and temperature. And we explored a little bit this idea of the number of gas molecules, also known as the amount of substance. But we need to take maybe a little closer look at what that quantity really is, N here, and also why we need the universal gas constant in our ideal gas law. So to start off with, let's take a closer look at this number N here. So looking at that number N, what is it? Well, it began with Avogadro's hypothesis. Amadeo Avogadro hypothesized that under the same condition of temperature and pressure, equal volumes of all gases contain the same number of molecules. So at a particular pressure and temperature situation, let's say that we're talking about this situation right here where we have a particular volume of a gas, let's say oxygen, O2, at this temperature and at a particular volume or pressure. It wouldn't matter if this were oxygen or if it were nitrogen, N2, even though they have different masses. It wouldn't matter as long as the same number of oxygen molecules were in the container, or the same number of nitrogen molecules in the same container, or even the same number of helium atoms. Helium is monatomic, meaning that it in itself is a gas. It doesn't need to be a molecule. So it doesn't matter what the gas molecule or atom is, as long as you have the same number of them, you're going to get the same volume temperature relationship or the same pressure temperature relationship. If you increase that number, then you're going to change things. So these numbers N right here are what we call moles. And that simply is a grouping of a certain number of entities. And these moles allow us to make these entities human-sized since atoms are so tiny. So, what is a mole? Now, moles can be cute, or moles can be kind of hideous. You have cute, fuzzy, furry moles, or kind of ugly moles. But the kind of moles we're going to be talking about are neither cute nor ugly. They're just simply a particular quantity. So, what is a mole here? Well, it represents an amount of a substance. It's kind of like how we use things like a dozen for eggs, and I'll get back to that. The mole is the amount of any substance that contains as many elementary particles, in other words, atoms or molecules, ions, electrons, as there are atoms in 12 grams of pure carbon-12. The isotope of carbon with atomic weight 12 has 6 protons and 6 neutrons. This corresponds to a value of 6.022 times 10 to the 23rd elementary entities of a substance. That's a big number, a 6 with 23 zeros. So, if we had 12 grams of pure carbon-12, and we could count up every single carbon atom within that 12 grams of pure carbon-12, we would end up with 6.022 times 10 to the 23 carbon atoms. So, how does that equate to a mole? Well, if I group any such particles or entities, then I have a mole of that substance. For example, 1 mole of oxygen, which are 2 oxygen atoms bound together. 1 mole of oxygen, these 2 atoms bound together would be 6.022 times 10 to the 23 oxygen molecules. So a mole is just a big grouping of a particular entity, typically atoms or molecules is where they're used. So, for example, with eggs, if we have 12 eggs, we call it a dozen. We don't care if they're medium-sized eggs or large eggs or extra large eggs. It's a dozen eggs. So, for example, in a mole of oxygen would weigh a lot more, have a lot more mass than a mole of carbon-12, because each oxygen atom is 16 grams per mole, and plus there are 2 oxygen atoms for every oxygen molecule. So 16 grams per each times 2 oxygen atoms is 32 grams of oxygen in 1 mole, where we had 12 grams of carbon in 1 mole. So mole is not mass. Mole is how many atoms or molecules there are. And that's what Avogadro's number is. It's how many entities there are in a mole. So again, 6 roughly with 23 zeros behind it. That's a lot of things. They can either be atoms or molecules or whatever. That's a lot of stuff. And so this is Amedeo Avogadro, and I put him on there because he was a very interesting looking character too. Moles and mass. To see the relationship between moles and mass, we have to look at a periodic table here. Let's focus on oxygen. Oxygen has 8 protons, and its most common isotope also has 8 neutrons. So other considerations, so forth, what we find out is that a big grouping of oxygen would have an atomic mass number here of 15.9994 grams per mole. So this is our translator between moles and mass. It is through this atomic mass number that you see here. For nitrogen, that atomic mass number is 14.0067. So 1 mole of nitrogen, in other words 6.022 times 10 to the 23rd nitrogen atoms, has a mass of 14.0067 grams. And likewise, fluorine here, 6.022 times 10 to the 23rd fluorine atoms, 1 mole in other words, has a mass of 18.9984 grams. Now, if we don't have singular atoms, if we have molecules, for example, if we have a carbon dioxide molecule, which is CO2, we have 1 carbon and 2 oxygen atoms making up that molecule, then we would take the atomic mass number of carbon plus 2 times the 15.9994 grams per mole for each oxygen atom, and we would get a total of 44.0095 grams per mole for a carbon dioxide molecule. So this number is actually called the molecular mass. So how would we find out the mass of 3.2 moles of carbon dioxide? Well, when we have moles and we want to find the actual mass, we would take the number of moles times the molecular mass and get the overall mass, in this case roughly 140 grams in 3.2 moles of carbon dioxide. Likewise, or kind of the opposite here, if we wanted to find the number of moles and we knew the overall mass of carbon dioxide, let's say it was 300 grams, we would divide by the molecular mass in order to find the number of moles. Finally, if you just have a particular element here and want to know the mass of it, the actual mass of it, and you don't know the number of moles, you can use what's known as atomic mass units. One unified atomic mass unit, the symbol for the unified atomic mass unit is U. 1 U is equal to 1.66 times 10 to the negative 27 kilograms. If you multiply that atomic mass unit times the atomic mass number, you would end up finding out the mass of a particular atom here. So, and then if we can compound that to molecules here, so in order to find the actual mass of a single carbon dioxide molecule, we can take the molecular mass of the 44.0095 and multiply by an atomic mass unit, and 1.66 times 10 to the negative 27 kilograms, and we would find that the mass, the actual mass of one carbon dioxide atom or molecule is 7.31 times 10 to the negative 26th kilograms. Wow, that was a massive amount of information. You might have to rewind this to check it out again. Let's see what my daughter's dog Ryder thinks of moles. Now let's look at the universal gas constant. R is the only thing that we haven't explained thoroughly in our PV equals nRT equation. In experiments, we can vary the pressure, volume, temperature, and the amount of gas. And so solving for R here by dividing both sides by NT, and varying these things in experiment, we get a value of 8.315, and no matter how we vary these variables. And so that makes it a very nice constant and is needed in our PV equals nRT equation to make things work. After doing several of these problems, you'll get very used to 8.315. Now, we have an interesting situation, and we don't always talk in moles. So for our ideal gas law here, we don't always use moles. Sometimes we know the number of molecules or the number of atoms in a particular case. So if we're talking about, and we really are counting up every single atom in a particular, or every single molecule in a particular experiment here, that's given the symbol N, number of molecules. So since the number of molecules is Avogadro's, the number of moles times Avogadro's number, we can translate, by knowing the number of molecules here, we can translate by translating our proportionality constant. Instead of using the universal gas law, if instead we take our universal gas law and divide by the 6.022 times 10 to the 23rd Avogadro's number, then we can create our new constant that can be used when we're talking about the number of molecules in our ideal gas law situation. Well, when we do that, we divide those two things out, divide our universal gas constant by Avogadro's number, we get 1.38 times 10 to the negative 23rd joules per Kelvin. And that is a new constant to be used when we're using this form of the ideal gas law equation. And that constant is known as Boltzmann's constant, K sub B. So this is used again when we're using this gas law equation in some of our thermodynamic equations. So we have two ideal gas law equations, and you just have to make sure whether you're talking in the number of molecules or atoms, or whether you're talking with the number of moles, which gas constant. So after all that, hopefully you can answer all of these questions. What is an atomic mass unit? What is a mole? What is the universal gas constant? What is Avogadro's hypothesis and number? What is Boltzmann's constant and why do we use it? And what are the two ways to represent the ideal gas law? And Scratch's parting exclamation. And good luck on your quest for continuous improvement.